let me call it epsilon I. So this is energy of individual particle. Particle number I is equal to minus mu times B times Si. So there is a spin up and spin down. And if you put system in the external magnetic field, then the energy of a given spin is equal to mu, which is the ratio of magnetic moment to spin, times B times Si. So now let's compute partition function. So we sum over all states.
That mu isn't the same thing as...
No.
That,
yeah, very good point. It's not the same thing. And let's...
Oh, yeah.
Mu. You can do mu tilde.
Mu tilde, yes. Very good. Thank you. Yeah, it didn't occur to me. The thing is that here we're going to do partition function. We're not going to do grand partition function. That's
okay.
Why. But yeah, you're absolutely right. I should not have used the same notation. Unfortunately, this mu is standard in quantum mechanics and electrodynamics. And that mu is standard in stat mech. So that's some flash of notation. But anyway, let's go with mu tilde. That's a very good point.
We don't have any
So we have a sum of states. And what does state mean? The state means that you sum of all possible values of Si. So your Si could be either +1 or -1, and it will be independent for every particle. So let me just write over states here, which is the same as Si, but just the stress with sum over states, e to the minus beta e. So this will be sum over all Si's, e to the minus beta epsilon 1 minus beta epsilon 2 minus ... That's exactly the exercise which we did here, which I just erased. So this is exactly the same two-state system which I was describing before. So you'll get a product, e to the beta mu b plus e to the minus beta mu b. Product over I. And this becomes 2 hyperbolic cosines of beta mu b, sorry, mu tilde b to the power of. That's exactly the problem which we solved before. But before I was telling you that this energy is equal to epsilon minus epsilon. But now, instead of epsilon, we have this mu tilde times s.
Is this n-1 the book though?
Huh?
Is this n-1 the book and then they approximated it in for reason for that?
Okay, it depends on your boundary conditions. I'm just taking the chain which has no boundary conditions. If you have,
and they said it was kind of
right.
It was very similar. They were considering a ferromagnet, but still with...
No, it's not about my ferromagnet. See, this, first of all, anything which is subregion in N wouldn't matter eventually. But they impose some specific boundary conditions.
Okay.
I think they impose periodicity or something like that. What do they do?
I swear there's not enough letters in the alphabet. Betas, B's, mu's. We use mu too much in physics.
What's that?
They overuse mu.
No. Sorry, this is different. Sorry. Yes, this is like...
Permeability,
I have
friction,
just a way
chemical
times-
potential.
So I have a way times S.
This.
Way times S1 times S2.
Kind of ran out of degrees. Greek
You're
letter.
looking at Heisenberg.
Greek
Yes, so
letter.
that might be the confusion. So the book does completely different system, which is much more complicated than this one. So they say, for me, the energy of individual atom, the energy of individual atom depends only on that atom. It does not depend on any other atom. What they have is energy, which is energy of two atoms interacting, which is equal to some alpha times Si times Sj.
Oh, and they're considering the boundaries at the end.
No, that the boundary is one thing, but also this is a completely different sum. Because now you have interactions between particles. I have just interaction of individual particle with magnetic field. So this is a much simpler problem.
Okay.
So the problem which you're mentioning is the Ising model, and there, of course, it's n-1. But that's because, so it's basically, yeah, so the reason to understand this n-1 is this. If I have n particles, if I just sum over individual particles, I have n terms. But now suppose I interact sum over nearest neighbors. how many neighbors I have. I have particle number 1, particle number 2. This is number 1. Then this is number 2, and so on. And the last one will be n minus first one. And if I have 2 particles, I have only 1 term. If I have 3 particles, I have only 2 terms, and so on. So I'm basically, it's like I'm counting the particles, and they're counting the spaces between particles. And they're all by factor, by 1. If I have n particles from a line, on a line, then the number of spaces is n minus 1. But again, this is a completely different problem, because they do it, they do Bayesian model. Here, it's much simpler. So, this is Z. Now I construct F. And then I construct df. So my df is minus s dt minus delta w. And why do I write w? So usually we write this term as pdv. But here it's more convenient. Here the volume is not going to change. What is going to change is the B field. So this work would not be mechanical work, it would be magnetic. And what is a magnetic work? So the magnetic work is minus, so minus s dt is there. And the magnetic work, as we discussed before, it's HdB if the V is kept fixed. So here I have n particles, I keep volume fixed, but I'm allowed to change the B field. No, there would be no hysteresis. This is paramagnetic, there's no hysteresis. In ferromagnetic there is a hysteresis. Here there is, everything is uniquely determined. So this is minus s dt plus V. And then what is this H? So here I will have to use a little bit of electrodynamics. My apologies to the people who have not taken it, but you can believe me that this is your H. And so you get minus s dt plus V. Let me continue somewhere else. So this is equal. Let me continue here. I will resolve that one. Wow. So again, what are we after? Our final goal is to find F, which we already did, but then to compute various things from this F. For example, we might want to know what the total magnetization is. So if you don't apply any external magnetic field, the total magnetization of your sample is equal to 0. But if you apply magnetic field, your spins want to orient themselves along magnetic field, there will be magnetization. So we might want to compute magnetization. So df, you can just continue this line because that's what I'm doing, is equal to minus s dt plus v dt of b squared over 2 mu naught minus vm dB. So why am I doing this? So first of all, I can define f tilde, which is equal to f minus v b squared over 2 mu naught. I'm multiplying by some. So notice this is temperature independent. So this is just, I'm shifting my energy level. So I'm going to 0 temperature. I shift my energy levels, and I can use different energy levels. Remember that F by itself does not make sense. It's, F only matters up to a constant. So I can definitely shift it by a constant. If this was time-dependent quantity, I would not be able to do it. But here I'm just shifting energy at 0 temperature, and the shift persists. So then I will find that df tilde is equal to minus s dt minus vm dB. And f tilde is as good as f. Because what I'm doing is I'm just shifting energy. I'm choosing my zero energy, energy equals to 0 at a different level. I can always do it. And it's crucial that it is temperature independent. So at 0 temperature, I fix my energy levels, and then I proceed. So from here, I conclude that V times M is equal to minus dF dB at constant temperature. That's what I was after. I want to compute magnetization. And this formula, along with this redefinition, allows me to compute magnetization. So now I just have to take this expression, differentiate it with respect to B, and I get my answer.
That's df tilde. Right?
Df tilde, yes.
Okay.
And F and F tilde, there's no difference between them. Here, for example, I could say that I'm computing F tilde.
Okay.
Because overall shift doesn't matter.
Okay.
See, this is proportional to temperature.
Right.
So, so this gives me effect what happens if temperature increases. So if there was some constant in this F, I could put it.
Right.
So this is equal to minus d over dB applied to minus kt over log z. This is my z. I take its log, I differentiate it. The algebra is given in the notes. Let me just write the answer. This is the answer. So we found magnetization. And this magnetization makes physical sense. So if my B is equal to 0, then magnetization is absent. And as my B increases, so the magnetization behaves like this. This is a B field. This is magnetization. And there is no hysteresis because the moment I know B field, I know magnetization. For given value of the B field, there is only one magnetization. And that's how the paramagnet is different from ferromagnet. For ferromagnets, for given value of B field, you would have different magnetization. For paramagnet, there is one-to-one correspondence. Every value of the B field gives me a given magnetization. Okay? So what happens if I change temperature? Suppose my temperature is very, very small. So if my temperature is very, very small, it means that this beta is enormous. So what it means is that this graph is almost vertical. So this is small t. On the other hand, if my beta is large, sorry, if my temperature is large, so if my temperature is large, it means that beta is small. So my function is tiny. So this is large t. So at large t, I will have almost no magnetization. For very extent, eventually, if I go to B field equal to infinity, of course I do get magnetization. But if I, let's say, fix some value of B field, and I change temperature, what I will see is as temperature decreases, my magnetization grows. As temperature increases, my magnetization goes to 0. Now you should tell me why it makes sense. Why does this answer make sense? Why would you expect that as temperature increases, your magnetization goes down?